All right, so today it's about the approximate nearest neighbors problem. It's also going to be a high dimensionality kind of point of emphasis. So yeah, I think let me just go over some of the stuff we've done recently. Maybe when concentration started was random graphs for us. That turned out to be turn off in disguise. We did some randomized rounding after that. We did online algorithms. Guess you'll play with that on your homework. And then we did last week distinct elements and F2 estimation. But F2 was really a vehicle to introduce the median trick. And then last time we did dimensionality reduction, also as a way to learn a lot about Gaussian random variables. Yeah, so dimensionality reduction actually turned out to just mostly be an expression of the fact that high dimensional Gaussian vectors, their length are incredibly well concentrated because they're basically sums of independent Gaussians. Okay, they're concentrated just like Chernov's stuff is concentrated. Okay, so today we're going to look at this approximate nearest neighbor problem, uh, which is very simple. Uh, you have a bunch of points in your database, and then you're given another query point, and you want to find the closest point, say in Euclidean distance. Okay. But for today, the point of emphasis will be doing this in very high dimensions. So this picture is a little misleading because it looks like it's in 2 dimensions. But in this picture, uh, the closest point looks like this one, right? So I guess we can draw some ball, and there's only one point at the boundary. Yeah. But again, we're interested in doing this in high dimensions. Uh, so this is something that actually has a lot of applications. Does anyone want to guess some? Yeah. Vector search. Okay, so but where's vector search used? Yeah. Just give me one application. Yes, vector database, yeah. But what do we use vector search and vector databases for? Let's not. Yeah, Google search. First of all, do people know how LLMs kind of work? But somewhere you're going to take text, you're going to try to predict more text, but somewhere in between, you're going to do a ton of regressions and stuff. There's going to be some vector representations, and because deep learning is going to keep kind of improving. So you have some high vector representation ultimately for every word, right before you finally take your word and guess the next word. You have some vector that kind of represents as much information as possible up to that point. Okay. So you train these vectors just based on this guessing the next word game. Okay. But these vectors turn out to be super duper useful. Okay. It turns out to encode a lot of information. So the vector right before you actually make a discrete guess, that's what they plug in. So you might take an Amazon product, and you take the whole product description, and you play the guessing game on it, but you extract out a vector from the inside, and that vector will be some kind of summary or representation of the review. You do the same thing with a query, and then you try to find which vector is closest to the query vector. Okay, and the crazy thing is it works. Okay, all right. So vector search. Any others? Yeah, so vector search with hidden representations. Any others? Latent representations. Yeah. Classification. Yeah. So there's also nearest neighbor classifier. So maybe all these points are labeled. Those are the geometry represents the x's, but they all have some labels y. And you say, I have a new point, and I want to try to figure out what its label is. Let me find all the nearest points in my data set and just take the most popular vote or something. Yeah. A traveling salesman. Uh, Not sure actually. Really useful for traveling. Yeah, traveling salesman has other problems just because it's empty hard. Uh, so you're not really too worried. This data structure part is usually not the bottleneck. They're willing to just say compute all the distance between all pairs because you're going to run some crazy heuristics anyway. Yeah, error correction, is that? Yeah, that could be. I mean, there are some. Okay, yeah, not exactly the techniques we use, but there is some. You have some bit string, it gets gargled over the wires, and you're like, what was this? But you try to look up, your codes, the things it could have been. Let me find the closest, say in Hamming distance. Okay. Another very important one early on was deduplication and kind of stuff. So they're crawling the internet. They don't know if they've seen the same website twice or if there's slight changes of the same website. Okay, so they would pass it through LSA to try to figure out which, the things the web crawler found were actually the same. That was a big one in the 90s. Okay. But it's used a lot, internally in the big companies. They just use this all the time. This is just bread and butter. Uh, yeah, best way to deal with big data. Yeah. Yeah, so I think for today's discussion, we can assume that the set of data is fixed, P is fixed, and you're just trying to find something inside. But I think the algorithm is going to be so simple that these other questions, you'll easily see what you could do. Okay. Now, okay, so that's nearest neighbor search. And we were discussing Euclidean distance. Another very popular one, including was vector search, which sometimes puts out normalized vectors, is angles. Okay, the angle between two vectors. Okay. Another one is Hamming distance if you're dealing with bit strings. That'll be on the homework. Okay. But for whatever geometry you're working with, you have some query point, you want to find the closest point. And depending on the geometry, you're going to use different techniques. Okay, so here's a warm-up. One-dimensional nearest neighbor search. So all your points are on a line. How can you build a data structure to fulfill nearest neighbor queries? Yeah. Yeah, just a balanced binary search tree, right? Every year I wish I had an even number. Okay, something like this. Okay, and this will just take log n time to find the nearest point. Is it bigger, is it smaller? Okay. All right, so that's fine. What if it was 2 dimensions? Yeah. Yeah, there's quadrants, essentially 2-dimensional analogs of binary search tree. You can, for example, split on the x coordinate, and split on the y coordinate, split on the x, split on the y. There's 100 different variations of this. Now, you can do this for 3 dimensions, 4 dimensions, 5 dimensions. What would be the running time of one of these queries as a function of the dimension if you took this kind of binary search plus plus approach? You guys know? Yeah. K log n, where k is the number of dimensions. That's a reasonable guess, but it's not quite it. Did you? 2 to the k log n. Not quite, but you're getting closer. Yeah. No, that would be better for larger k, not log base k. Huh? What? No, it's not 30 to the k log n. No. So those data structures are going to grow like log to the kn. It's basically a binary tree multiplied with a binary tree multiplied with a binary tree. But the key point is this works great in low dimensions. They'll still use this in computational geometry a lot, right? But it won't really work for these kind of big data, internet scale things. Okay. All right. So, so that brings us to this idea of locality sensitive hashing. So normally when we talk about hash functions, you know, what do we want the hash functions to kind of do with the keys, right? What do we want it to do? Well, like what was bad before? Collisions, right? We really wanted things that looked like they were spreading things out, uniformly at random or something, right? It was relatively few collisions. But before, like more random was better, right? We expected better bounds for 4 wise independent and 5 wise and 6 wise and so on and so forth. Okay. Today we're going to do sort of the opposite, which is sort of interesting. Okay. We want to find hash functions where nearby points are more likely to collide. Okay, so still be hashing because there will be kind of very simple functions that you can apply to your point. It's going to output some index. Okay, but we actually want a particular kind of collision, right? Because why would this help for nearest neighbor? Yeah. You just hash it, and then you'll see which ones to check. Yeah, so we want to develop these algorithms where first you kind of hash all your points and you fill them in some table. And then you take your query point and you compute the hash and you just look in the cell and hope the nearest neighbor is in there. Okay. But of course it won't be the exact match in general. But you're hoping if they're nearby, they'll land in the same table. Okay, so it's a very clever sort of opposite application of hashing. And then you can see why this has immediate appeal, in the real world, in distributed settings, systems considerations where there's all these complicated things, because it's so simple, right? You can run this in any system. Yeah. All right, so we're going to start with the angular setting, where the input, okay, there's a two-dimensional picture, but at some level, you're really on the surface of a d-dimensional sphere. So I'm just worried about the angle between any two vectors, so we can assume they all have unit length, so they're all sitting on the surface of a sphere. And of some high dimensional uh, sphere. Get these arrows. Okay. Which of course, three-dimensional picture is also kind of a misrepresentation, but I think you get the point. If you look at any two-dimensional slice, uh, it'll look like this picture in the middle. Okay, if I project onto two. Okay. All right. So I want, if I query again, granted it's in two dimensions, like this point here, the nearest neighbor should be this because that's the closest in angle. Okay. All right. So now we want to come up with some kind of hashing scheme, right? Um, some way of putting these things into buckets, where things with small angle are more likely to be in the same bucket. Yeah, any ideas? Like small differences in angles. Yeah, you want small differences in angles to be more likely to collide. So you need to somehow, partition the data, right? But it should, yeah. Okay, so how should I partition? Okay, I see some violent. Okay, so for example, suppose I just want to do two buckets. Okay, so maybe something like that. Uh, okay, so actually, let me do this again. Oh man, there we go. Okay, so I saw a lot of people making line-like motions. Okay, so I can draw like a line like this, and that sort of splits things in half if I can extend it down or something, right? Uh, but where should I put the line? Oh, uh, something based on the data. So the suggestion was, oh, can I try to find a line that sort of balances these two things? Um, okay. One thing to be a little bit worried about is that it's not clear that it's so easy in high dimensions as it is in low dimensions. Yeah, any other ideas? Yeah. Did you like pick a random vector and then do the dot product of all of them and then categorize them basically the same? Yeah, so we can just spin this around. Okay, and we'll pick a random direction like that. Okay. And now how do you actually split it in half? Well, one way to do it algebraically is you take the dot product, which is really projecting onto this line. Okay. So that's taking the dot product, and that number will either be positive or negative. Okay. And it's going to split exactly like at that right angle. Okay. So over here will be everything that's bigger and everything that'll be smaller. Okay. In the dot product projection. And you can already see intuitively uh, that, it's kind of less likely to split apart things that are close together. Things that are opposite will like always be split. Okay. So Okay, so let's try to formalize that. Now, when we do analyze this, we're not going to like we're going to do when we analyze it, we're going to do a parameterized version. So in other words, I'm going to fix a particular angle. That's sort of, for the sake of discussion, my definition of near some parameter theta. Okay, and my goal is either, and there's going to be some double-sided error, given a query, output something within a constant factor of theta, or declare there's no point less than equal to theta. So if there's stuff in between, either answer is okay. But it's really saying if there's a point that's within angle theta, you should output something, say within a constant factor of theta. We need a little approximation. Okay, so we'll focus on a single threshold at a time. Okay, now I want to suggest that if we can do a single threshold, then we can solve the original problem of finding nearest neighbor. But how? You can do binary search, right? You might start with theta even as large as pi. It'll find something, and then you go to pi over 2. Is there anything? Yes. Okay. Pi over 4. Is there anything? Yes. Eventually, you'll get so small that I couldn't find anything. Then you go back up. Yeah, and then you do binary search. So if we can do a single threshold theta and prepare a data structure for single threshold theta, then in the actual query, you can just binary search over them. Okay, so I won't put too much emphasis on that back end. We'll just focus on one of these individual thresholds. Okay? In the homework, you'll get to, for your particular, you'll do Hamming distance, and for that one, I'll ask you to also work through what it would look like on the back end. Yeah, random or arbitrary? Uh, yeah, probably anything. You might be able to take it down to 1 plus epsilon and pay for it. Yeah, so I probably just chose something nice 3 years ago. Okay, good. Well, I think it'll be clear from the analysis if it goes all the way down to 1 plus epsilon. So we'll see. Okay, so here's maybe the key thing. So let's just focus on picking one. Okay. Here's actually a good question. How do you pick a random direction on the sphere? How do you pick a random point on the sphere? Okay, so if you picked, we can even do this in 2 dimensions. Suggestion was if you pick something from this square, well, that's the outer part of the square, and project, and then just normalized it, would that give you a random direction? Right? Because clearly, like this one going out to the corner has a little bit more kind of margin, right? More space. I don't know if area is the right word, but yeah. So, okay, so that won't quite work. You can't just sample from the hypercube containing the circle. Yeah. How do you pick some random angles? Oh, I see. Uh, oh, that work? That might actually work. Yeah. Sorry. So you're trying to pick a random direction, and what was the idea? To R's one. What's R? Oh, but you're in high dimensions. Yeah. Oh, okay. Some kind of rejection sampling. Okay. Uh, but now I think one has to be careful about the volume of the circle being. Yeah. Yeah, so I'm not 100% sure about the previous suggestion of just directly sampling the angle parameters. I just don't want to make a mistake. But one thing that definitely works, we learned last time that the Gaussian distribution is rotationally invariant. So if every coordinate of the vector is sampled from the Gaussian, that will actually, and then you normalized it. that would actually not be biased in the way that the hypercube was. Okay, so that's what we're going to do here. Now we just need to analyze. Okay, I have two vectors, and I pick a random Gaussian, and I do the projection onto it, right? And I want to know what are the odds they're going to get the same hash code, which for us is the sign of the dot product. Is it positive? Is it negative? Okay. All right. So the claim is that it's something proportional to the angle between them. Why? I'm glad you suggested that. Can we just look at the 2D? So once you focus on X and Y, you can just focus on the two-dimensional space spanned by them. Yes. Yes. Because you're still going to be choosing a random angle on this. And the other dimensions, X and Y, are going to be orthogonal to anyway. Everything is rotation invariant. Okay. So now what are the points that could split it? Diameter? Okay, so if it went here, then everything would still be positive, right? If so, I've also in the dotted lines represent the 25 quarter angle thing, right angle stuff. Maybe I'll make a different color so it's easier to see. Let's do purple for X. Okay, so that represents that kind of half, whatever. Okay, so if my random vector was here, would they get the same hash code? Everyone but one person says yes. Okay, so here they're both gonna be positive there. Okay, what about here? They'll both be projecting positively. What about here? Okay, so now X is still positive, but Y is actually negative. Okay, what about here? Yeah, they're both be negative. How about here? Both negative. What about here? Okay, what about here? No. What about here? Okay. So the bad region is here. Okay. And that's sort of at these right angles to the original lines. And that's why you get exactly, it's really 2 times this angle divided by 2 pi, because that's the whole circle. Okay, because it's 2 pieces of this pi. Make sense? Okay. So this is totally what we want, right? The odds of missing are proportional to the angle. If it's very far angle, it's more likely to miss. That's what we're looking for. Okay, good. All right, now how can I strengthen my hash? Because I really, really want to increase the odds of non-neighbors missing and increase the odds of neighbors colliding. Yeah. Yeah, we can do this many times, and then you get this big hash code: 1, -1, 1, -1, 1, 1, -1, -1, whatever, right? Okay. So we can do it several times, and then we can group by hash code. So we'll figure out how many times we should do it in a moment. But the high level idea is we draw k random directions. That gives us our hash codes. And now the data structure itself is just going to look like a table. All the points of this hash code goes there. All the points of that hash code goes there, so on and so forth. Yeah. Oh, okay. So s to the d minus 1 means d-dimensional sphere. You lose 1 degree of freedom because everyone has length 1. That's why people sometimes call the circle is treated as a one-dimensional object, the surface of a circle. Okay, that's the d minus 1. But that means it's the sphere in d dimensions. Yeah, they like to keep you on your toes. Okay, so but does the data structure make sense? We're going to do a bunch of random Gaussian vectors. That gives us a hash code, and we're going to just dump them in the bucket. If I want to query, I go to the bucket, and now I have to scan all the points in the bucket. Okay. All right. Good. Any questions? Yeah. Okay. So we might fail. It might fail. Yeah. So we're gonna have to figure out how to balance. Um, we can answer that now. Suppose I'm hashing so much. What to do about the situation where it just messes up and it split apart? It split you from the actual near neighbor. What should we generally do for that kind of scenario, which could easily happen? How do I decrease the odds of false negatives? Sorry? Repetition. So we can at least, if this data structure is only right sometimes and is generally fast, we can repeat it until we feel more confident. Okay, so we'll explore that. Okay. Okay, so now let's do some analysis. Okay. So suppose you have a near neighbor. I want to show that the odds of them colliding are pretty good. Okay. So, okay. So what's the probability that h of x is equal to h of y? What should I write? Yeah. Angle xy over k pi to the k. 1 minus. 'Cause that's the odds of it not colliding. The pi over pi was not colliding. So this means it collides. It needs to collide k times. Okay. And now what? Yeah. Oh, we could replace with theta. So this is less than, so this will be greater than or equal to 1 minus theta to the k. We want to bound this below, right? So that's good. We want to show the odds are reasonably good. All right. Theta over pi. Okay. Yeah. Yeah. So the nice inequality, of course, is 1 plus x is less than or equal to e to the x. Here we want the other direction, but as like a general rule, I don't want to go into it too slowly. Is going to be greater than or equal to e to the x minus some quadratic term, some constant times x squared. And I'm really only interested in the small theta. So I'm going to just be a little bit lazy, and I'll write kind of greater than e to the minus theta over k times k. Oh, no, sorry, that's not a k. I can't read my own handwriting. Okay, e to the minus theta over pi times k. Okay, I'm really missing like a quadratic term here, but that will be dominated by the linear term. Okay, okay, so we have some preliminary analysis. It's roughly okay. Now, what happens when the angle is bigger than 2 theta? Now we'll do the probability that h of x is equal to h of y. Now we want to show that this is kind of low, right? So, well, yeah. The first step will be the same because this part's exact. Right? And now, yeah, huh? Okay, well, oh, to the power k. And then, okay, we can use it right now. Angle xy over pi times k. And this is I put this in. Something like that. Yeah. Okay. So the one is bigger than e to the minus theta. Okay. Uh, good. Oh, how is okay? So the expected number of false positives, right, will be this times n. So this will be less than or equal to e to the negative 2 theta over pi k times n. Now, if I wanted this to be at most like 1 or a constant, right? I want to make sure that when I look into the bucket, I don't spend too much time looking at junk points. If I wanted this to be less than or equal to 1, then what might I make k? Well, there's a negative sign, so it's not log over n. I think just log n will be fine. It'll be something times log n to get rid of the n. What goes in front of it? Pi over 2 theta. So if I choose k is equal to pi over 2 theta, then I shouldn't spend waste too much time looking at false positives. Okay, good, good. So if we choose that, and I plugged in from before, so before we had this theta instead of 2 theta, so instead of get 1 over n, you're going to get 1 over square root n. Okay. So now we have a data structure that looks like this. Okay, so if I repeat uh, that quantity we just came up with in my hash code, uh, we expect to collide with 1 point, but we'll actually find a near neighbor with probability 1 over square root n or something, right? Okay, yeah. Does it actually generate a normal, like the Gaussian? I think. Okay, so how hard is it to generate from the Gaussian? Uh, well, I'm sure that people who take it very seriously, there's like a whole detailed thing. At some level, it's not too like I think you can just use whatever your computer or Python library provides, and it's not a big deal. But I think for us, the critical thing to point out is that we only have to generate the hash vectors once. Then we use that for all the input, right? So the fact that the number of Gaussians we're generating is independent of the input size n, number of points, which is really the painful point, is why we're not even concerned at all. But in general, I think people find this very reliable, and you should expect that, like, if somehow your computer is actually like slightly off in the distribution, then our calculations will still be pretty robust, right? Because we'll be slightly off. It won't be exactly this probability, but it'll be something proportional to how far off the implementation is. So, like, this implementation will be robust. If the distribution was imperfect, our thing will be imperfect, but not in a way that's going to blow up in your face. I mean, I'm sure we can do the error analysis where we just expand out epsilons. Okay. Good. Okay. So with the right parameters, you get a true positive is probably 1 over square root n. And you get one false positive in expectation. Okay. But this gets back to the original question. Okay, that means most of the time you're not going to find a near neighbor, even when there is a near neighbor. So what should we do? So the problem is that you're going to get a lot of false negatives even when there is a positive, right? You're going to turn up nothing, turn up nothing. So how do we address this? Yeah, we'll just make this data structure square root n times, or maybe square root n times log n, just for fun. Okay. Right. So if you repeat square root n log n times, this whole data structure square root n log n times. Now what? When you query, how long does it take? Well, square root n times, each of your inputs is going to have to do like k projections or something, like so square root n, d times k, where k is this value. Plus, you compare to at most 1 point on average each time. So you spend, d time doing the dot product. What is that? Okay. Of course, d could basically be at most log n from last lecture, but that doesn't matter too much. Okay, but the key point is now to find the nearest neighbor, you're not looking at all the points. You're looking at square root endpoints. Okay, in this probabilistic data structure. Make sense? Okay, good. So we get a sublinear search algorithm. All right, any questions about the angular LSH? I think the book will write out the full balance cleanly, but you just repeat and you get what you get. Guess the square root n log n with the log between friends. One thing to maybe point out is our data structure uses superlinear space. Well, yeah, depending on how you organize it, but at some level, each of your points is sitting in square root n tables. You've actually blown up your input side. But in practice, like every hash bucket could be sitting on a different computer in a big network. So space is free. Okay. Any questions? Yeah. Oh, you still do the you still measure the distance between two vectors. They're d-dimensional. Just do a dot product and take the cosine or whatever. I guess d is smaller than dk, so it's not such a big deal. dk just comes from computing the hash. Any other questions? Okay. All right. Now let's do Euclidean LSH. Now we want to get the Euclidean distance. Again, it's in high dimensional, so the picture is slightly misleading. Yeah. Uh, maybe better. I don't remember. The angular LSH is simpler than the one coming up next. The one coming up next won't be optimal. Angular just might be optimal. It's just so simple and clean. But in any case, it can be Googled. There's also a whole world of heuristics. Like, yeah, there's people whose life is doing LSH, and they might do some clustering first for really, really close things, and then throw LSH on top, and this and that. Just all kind of graph. There's a lot. There's a whole world, but yeah. Any other questions about the angular case? Okay. All right. Now we're going to move on to the Euclidean case. Okay, so now you're just trying to get a Euclidean distance between 92 points. And we're going to do the same game as before. For some reason, I used R and sigma here. I think we'll just make that 1. But before that was 4. Random or arbitrary 4. But same game as before. Either you find something with Euclidean distance, at most 2 times your target, or you declare that there's no point within the target distance. Okay. Once you can do that, you can do binary search. Yeah, and then this is all kind of scale invariant. So we can make our lives easy and assume that target distance is 1. Right? We can just rescale the input. Okay, good. All right. Any ideas? Any ideas for yeah? Okay. Balls and shells. Uh, yeah, yeah, that's definitely a possibility. Um, Maybe there's some question about how many shells you need. But okay, so maybe one idea is that I can try a bunch of shells at various distances. So maybe like distance radius 1, radius 1 plus epsilon, radius 1 plus epsilon squared, 1 plus epsilon cubed, and so forth. And then for each, try to throw an angular LSH on top. One needs to check. Yeah, that's certainly possible. But for example, one needs to make sure, for example, that uh, there is some value of 1 plus epsilon that, I mean, it's not clear that you can get maybe you have to do very fine shells at some point. One has to at least check this. But otherwise, conceptually, it's possible. I wouldn't rule it out, but one has to at least figure out, if you want some sort of approximate distance, how many shells you need to make, kind of how fine grained they need to be, whether they can follow a nice geometric progression like 1 plus epsilon, that would be just fine. That would be my first guess, but one has to at least push that through. Okay, so maybe one possibility is to try to reduce to angular. Yeah. Okay, so can you do a grid? Okay, so uh, one sec. This is going slowly, but I have some tricks. We can create grids at an exponential rate. Okay, gonna throw a grid on top, something like this. Yeah, that looks pretty good, huh? Okay. No, we have better tricks. Check this out. Wait, that's not what I wanted. Okay, one sec. Okay, we'll just do it horizontally. Okay, so let me talk while I draw. Um, uh, okay, so you could try to throw a grid on top. Now, one thing to be worried about, the grid is just fine in 2 dimensions, but how big does the grid start to get in high dimensions, right? So that's one thing to worry about is that these grids are going to blow up on you. Okay, so the grids are actually implicitly not that different than the quad tree idea, because at the bottom of the quad tree you basically have grid cells. Um, yeah, but that's so this is a very natural kind of computational geometry, low dimensional geometry kind of idea. Why don't you? Uh, okay, but certainly at the level of this picture, um, I was trying to, but then you have to reselect it with the lasso, and then that would require selecting all the red points. Trust me, I'm like the world's greatest notability expert. It's impossible in the circumstances. Huh? Oh, another cool trick is you can copy and paste the whole thing before you start. Yeah. Okay. Okay. So you could do something like a grid that we painstakingly drawn. It's not so bad. It's a natural low dimensional geometry idea, but this will suffer the curse of dimensionality, so to speak. Okay? Yes, part of the problem is that this is only drawn into 2D, so it's a little hard to imagine. Yeah. So you could put it into log n dimensions and throw it into a quad tree, but what would be like the query time? It would be like log to the log, right? Yeah, it's bigger than any polynomial, right? 2 to the log is a polynomial. So it'll be super polynomial. It'll be sub-exponential. Yeah. So this is sort of like a data-dependent clustering idea. We try to pick some centers, grow some balls, put them in, grow some balls. So there are vector databases that take this kind of approach, this hierarchical, navigable, small world thingy, but there's not much you can prove about those. But that is a popular heuristic. So that's a data-dependent approach where you maybe sample a few things to get you started, and there's no like roots in the tree, and then you recurse and stuff like this. Yeah. Okay, so maybe this picture is not great because it's only drawn in 2Ds. But suppose I wanted to go from like 2D to 1D. I really want to go from high D to 1D, but in this picture it's 2D. Yeah. Okay, so we can do a random line. It's a grid spilling over. Okay, something like this. Okay, and I could project all the points um, onto, oops, onto the line, something like this. Okay. All right. Once I project everything onto the line, then what? Now you have some points on the line. How do I turn them into hash buckets and codes? I just split it in half. That's a possibility. Now that starts to look like Angular, right? Because we're just looking at positive and negative projection. We're gonna do something a little different. Any alternatives? Because Angular might still work, but yeah. Oh, some data dependent thing. I mean, at some level, you can even build a whole binary tree over this. I want two features. I want something that looks like a hash code because it's nice for practice. And I want to do something that's like relatively oblivious. I don't really want to analyze the whole data. Like last time for Angular, we didn't really analyze it. It was basically oblivious. Yeah. Up versus down. That's like the Angular one, right? Positive or negative projection. Yeah, so that's a possibility, but what's so okay, the one we're going to explore is we're going to bucket it. Sorry, I thought this was going to be great. Okay. So we're going to bucket it like this. Okay. So you pick a random line and you're gonna chunk it, and maybe this will sort of like if we're going for distance one, this could be one or something. Something proportional to our near neighbor distance threshold we're going for. Okay. Now, how should I actually set the buckets? Like I could get them to line up at like the origin, like this, right? But we don't want to do that because maybe there's some data that's bad for that, right? Because things that are just around the origin are always getting killed. Yeah, so we're going to randomly translate the buckets and pick a random translation to set it. Okay. So we project onto one line, and then we randomly translate the buckets. That makes sense? Okay. So it'll look, this is sort of equivalent. Pick a random Gaussian is basically going to have unit length anyway. You project it, and then you add this random translation alpha. Okay. All right. Any questions about the algorithm? So that'll be just one. Yeah. Yes. Yeah. So I mean, it looks good in 2 dimensions, but in high dimensions, like your random vector is going to be orthogonal to almost everything. A lot of points are going to get very close to zero and stuff. So yeah, we'll need to amplify and figure out the right balance. So we'll do some preliminary calculations, one line first, and then we'll figure out. Yes. Oh, that's rounded down. That's like a floor. I guess it still looks like an L. Okay. Yeah. Huh? Yeah, so otherwise, well, basically randomness is good. I mean, we'll see why it's useful in the analysis, but like if it was always going to be like exactly like this, and I wanted to choose a bad input, I would try to choose things that, might get split by the, because okay, something like this, they might be very close, but they're going to both project to very close to the origin, right? And then it's going to get hammered. So yeah. So we just don't want it to be, we want it to be good for any input. Yeah. Um, well, I think we'll see in a moment where the translation helps in our analysis. Whether you can do without, I don't think you can, but let's at least see why it's useful first. Okay. All right. Actually, is that happening right away? Yeah. Okay. So that's going to happen right away. At least going to make our analysis easier. So this is going to be conditional on your direction. Okay. So conditional on choosing that random direction or Gaussian vector. What is the probability that these hash codes are equal? The claim will be the max of 1 minus the absolute distance along the line or 0. Okay, so just to be, what does this quantity represent? Uh, so you have this line, G, X is somewhere, Y is somewhere, okay? And this difference here, that's X minus Y comma G, yeah? Because here on the line, this will be Y comma G. And here, this will be X comma G, okay? So, okay, good. Um, Now, what are the odds that things get split up? Yeah, so only if the divider falls in between here. Okay. So if this thing is bigger than 1, it's always going to get split. So that's why you have 0. When it's less than 1, it could be anywhere in here equally likely where this is a whole span of 1. And only if it's inside here, it gets killed, gets split up. Okay. So that's just like a simple put it on the line, and that's what it is. Okay. All right. Good. All right. Now it gets a little more technical looking. All right. So now, okay, the probability, the h of x is equal to h of y, okay, is going to be something 2 over the distance, 1 minus t, the integral of 1 minus t, times the density of the Gaussian random variable t over norm of x minus y. Okay, this is a very unsatisfying claim. I should point out that that quantity, we'll use it in a moment, is decreasing in norm of x minus y if you crunched it through. Okay, which is what you want. When 2 points get closer together, you want the odds to go up. So this will get dominated by this, I guess, thing that's getting smaller, and thus the whole thing getting bigger. Okay? The density is always stuck between 0 and 1 anyway. Okay, so let's do this ugly proof. This is the one ugly proof. All right. Okay, so uh, so I shouldn't have used G twice, but this projection, right? This will be a random sum of Gaussians. Or sorry, it's a sum of Gaussians given by x minus y. And as such, it's another Gaussian. But the variance looks like this. Okay. And if you related the density of a Gaussian was a particular variance, was the Gaussian of the density of a Gaussian was unit variance, you'll get this kind of relationship. G of t is equal to 1 over that standard deviation, f of t over the standard deviation. Okay. This is like plugging into that awkward e to the minus x squared over 2 thing. So we'll just take that as given because it's not that fun to double check this. Yeah.
So f of t is just like the probability function.
Yeah, the density function, the thing that goes inside the integral for the unit variance Gaussian, the normal one. Okay. Okay. So now what's the probability that h of x is equal to h of y? Let's just go through it slowly and condition on the direction. Okay. So, or on the, sorry, the location on the line. So, okay. Probably h of x is equal to y given that this thing is equal to t, and then the density function of t. Sorry, yeah? Negative? Which where should it be the negative sign?
Why is the integral from 0?
Oh, it should be negative infinity. Yeah, it's going to be corrected in a moment. Good. Uh, let's write it this way. So I'm going to, since our lemma uses absolute value, I'll put an absolute value here. Now I'm just going from 0 to infinity. It's the metric, and I'm doubling. So the negative 5 is just counted on the 5 side. Negative 10 is counted on the 10 side. Okay, so instead of doing this quantity being equal to negative 3 or 3, I'll just focus on it being equal to 3 and double count it. Okay. Okay. So from here, I think we just plug in our lemma from before. Okay, so our lemma says this thing is either 1 minus that distance on the line all the way down to 0. Okay, so that means we're going to truncate our integral to 1 because beyond 1, it's always getting split. And then otherwise, you just get 1 minus t times this density function. There's nothing actually that interesting going on in this lemma. We're just kind of plugging in some definitions and plugging in our lemma. That previous lemma is where the actual geometry happened. Okay, and at some level, there's like a whole lot of pain going on inside this density that I don't want to write out. Okay, all right, so good. All right, so this is where things get a little bit unsatisfying. But so sigma is our like error thingy, right? Like factor 4, factor 5, or whatever. So okay, so p represents the collision probability when that distance is less than or equal to 1. So for the near neighbors. Okay, so it's just plugging in x minus y is equal to 1. Since that function is decreasing in the distance, uh, equal to 1 is sort of the worst case for it. Okay, and then up here, this is the odds of colliding someone that's strongly not a neighbor, at least sigma times sigma distance away. Okay, and so the worst case is when the distance is exactly sigma because it's decreasing in the distance. And this is just plugging in. So again, nothing deep. It's just some symbols floating around.
Should be greater than the signal and this is also less because of the
So we want greater than equal. So so we're going to look at two factors. This is the odds of getting that true positive. There's a near neighbor, the distance is less than 1. And these are the odds of false positives. So these are things that are further than distance sigma. So I don't want to return them. And so I'm hoping that I don't collide. Yeah. Yeah, okay. So that so that's why greater than equals sigma. So these are everything that's really far away. Sigma is some factor bigger. This sigma is the arbitrary 4 from before. Okay. All right. I can tell you guys are as excited about these integrals as I am. Let's keep going. Okay. Now, in the algorithm, we'll do the same thing as before. We're going to group all the points by the hash code, and then when we query, we'll scan everyone in a bucket and actually get the exact distance to everyone. Okay. So the probability of even finding your point, if one exists, is p. Whatever p is, 0.3 something, right? What's the expected running time of this algorithm, as is? As functions of p and q. So we won't even open up what q is explicitly. So the algorithm is going to query something, and it's going to look at all the points in a bucket. So how long will a query take? Why? Oh, so this so assume this is the entire. We haven't done any amplification yet. We just have one data structure that just does this once. Okay, and for that we have this particular p and q. So this won't count repetition. So even if you're not repeating, you're just doing one pass. How long would it take? Yeah. So p times the number of neighbors, and for each of those you do a dot product. So maybe p times something times d. D is for measuring the distance. But what else do you have to pay? Collisions. So how much time do you spend on collisions? These are false positives. Q. Q times n. So everyone else represents noise. So here I guess I'm treating the distance measurement as a constant, but you could have multiplied it by d. for the actual. Okay. Okay, so if you want constant probability, as was suggested, you repeat 1 over p times. And now your expected total time will look something like 1 over p plus q over pn. Yeah.
One instead of like p times the revolution. Oh, it's never mind. For the expected time.
Okay, so one thing you can do is like if your data structure finds something that's good, you can just exit right away. So you should only have to deal with one positive anyway. So instead of doing pn, you can just do p. Because as soon as you find one, you can just stop comparing.
Once you stop with these the collision, it's oh, I guess never mind.
Good, yeah, you want to keep looking at the bucket to see if something good will come. But once you find something good, you can just stop. Okay. Now I want to focus on this. So our running time really is this q over pn. Okay. And 1 over p is not a big deal. So what we really want to do is try to figure out how to improve this q over p to a more favorable fraction. Okay, so we have the kind of the basic parts of our data structure. Now we just want to kind of tune it up.
Is q a constant?
Well, q is a constant once sigma is fixed. Q is a function of sigma.
Wait, what was second?
So our algorithm is just how we're defining your neighbor. So Q sigma could be 2, meaning that don't return anything that's more than a factor 2 away. So I'm going for, if sigma is 2, I'm going for a 2 approximation. So the question is, at some level, we have an algorithm that runs in Q over Pn time, 1 over P plus Q over Pn time. Just when we have the bare bones algorithm to do this. Now I want to just do some fine tuning and figure out how to improve this. And the critical part is kind of this. Yeah.
Like the points that you already like checked are far away and just not have so much.
We'll change our data structure in a deep way. So what do we know about Q over P?
We came from having one line.
Sorry?
We came from having that one green line.
That's true. That it came from a green line.
Green line.
Right, right. So in particular, which is bigger, Q or P?
Well, we must see.
Assume sigma is bigger than 1. So what P represents the probability of something close colliding. Q represents the probability of something far apart, a factor 2 apart colliding. So which one will be bigger? Hopefully P, but in fact that function is decreasing in the distance, right? So it is P. Okay, so this fraction is something less than 1. And I want to make it really small because I'm paying some constant times n right now, right? Okay, so how can I get that term really small?
You add more green lines.
We're going to add more, we're going to amplify. Okay, so we'll add more green lines. Okay, so we'll just have a bunch of these lines and a bunch of these hashes. Okay, and if I do k of these, then when I start recalculating P and Q, you start getting something like this. I forgot the dt. Okay, it's just multiplying things by a factor of k. Okay, so in particular, in terms of the original P and Q from before, when I have things that are close by, what are the odds of them colliding? It's at least. Not a trick question. It's at least P to the k. And then the ones that are far apart, the odds of them colliding are at most Q to the k. Okay, nothing deep. But now when we go back and we do the exact same calculations, now my probability of success is P to the k. And just one of these, with just more hash bits takes 1 plus q to the kn time in expectation, right? So we're really driving down the false positives. Okay. Now I have to repeat in proportion to the success probability. So repeat 1 over pk times, and now you get something like this. Okay. So just by repeating, we can start doing chipping away at this dominant term. Okay. At some point, p over q to the k starts to equal 1 over, this term starts to equal that. And that's how we should set k. Okay. So, good. Okay, so the expected time, what did I hide behind here? Uh, okay, the expected total time is really, there's a factor of k here because you also need to compute the hashes. There's k of them. For each of these, the inner hash. So each. Okay, so we have 2 layers of amplification, right? We took one green line and we turned that into k green lines. So now one hash code really consists of k numbers. And then we take that data structure and we repeat it 1 over p to the k times. Okay, so this k represents one hash code from one instance, and then it gets repeated 1 over p to the k times. Okay, now, okay, that you can write like this. Okay, and okay, what is the arrow is kind of confusing. I feel like there should be something like this, but I might erase it. Okay, so if I want q to the kn equal to 1, what should I make k? Yeah, something like this. Okay, you can do that on paper. That'll make that term equal to 1. And then what's left? Okay. Okay, so once that's equal to 1, now you just have to worry about k times 1 over p to the k and plugging in. So you get k 1 over p to the k is equal to log n log 1 over k n to the rho of sigma, where rho of sigma. Sorry, which is the most controversial handwriting moment?
Still looks like signal.
Oh, this sigma looks like a 6.
Yeah.
Okay, I'll explain why we like this notation. So, but it is important to point out that this expression, this is just something from the exponent that we gave a name, right? If you did this slowly, it's not hard to get. Okay, but you wouldn't want to watch me do it slowly. It is good to point out that this log 1 over p, log 1 over q is strictly a function of sigma. Okay, so at some level, these terms are not so significant. There is a q sitting down here, but there's a log around it. It's not the end of the world. You're really concerned about what's the exponent on n, right? This is going to dominate your running time. That's why it's kind of written like this. Okay. All right. So that's actually the whole analysis, believe it or not. We don't go further. So maybe let me show it like this. Okay. So what do we show? By doing this random line and then kind of repeating the random line for one inner layer of amplification and then repeating that whole thing for an outer level of amplification and kind of choosing those parameters correctly, we've shown that you'll spend something like n to the rho of sigma time, where rho is some function of sigma. Okay, and so the question is, what the hell is rho of sigma and how do you make sense of it? Right? You'd think you could try to simplify and come up with a closed form solution. At one point, I thought I did, and I realized a year later it was completely buggy. Okay, so what do people actually do? They just plot it. Okay, so what does that mean? So if you were going for a 2 approximation, okay, red's okay. So a 2 approximation, and that looks like it's something like 0.61 or something. Okay, but what does that mean? You're spending n to the 0.61 time for a 2 approximation Euclidean LSH. In particular, you're spending much less than n. Okay, and anything all the way down, you know, if you want to get a 1 plus epsilon, it'll be close to n to the 1, but it'll be n to the 0.9 something. Okay, so that's actually the state of the art. Well, I mean, you could do a little bit better than this, but the state of the art for this analysis is actually you're left at the end with a somewhat uh, dissatisfying but correct plot to tell you exactly what the exponents are. Okay? But at some level, it's not too important. What really matters is that you're doing much better than scanning the whole thing. And it's also fantastic that it's very easy to implement if you're doing it, you know, if you're Google and you just have a massive server farms of second grade computers, this is perfect. All right. That's actually it for this lecture. I just want to mention this is something that works really well in practice. Yeah. Yeah, that was clean. But that was 4 approximate or 2 approximate.